Let's break down the core idea behind this paper. LoRA, low-rank adaptation, from Microsoft. Here's a magic trick. This is a 175 billion parameter model. To teach it a new task, the old way makes a whole second copy of it. All 175 billion numbers, just for that one task. LoRA does the same job by saving a file you could email. Same model, same quality, and the task-specific part shrinks from 350 gigabytes to about 35 megabytes. Let's see how. Fine-tuning means take the pre-trained model and nudge every weight until it's good at your task. It works. But now your customized model is as big as the original. And if you have 10 tasks, you're storing 10 full copies of a giant. That's fine for a hobby. It's a nightmare when the model is enormous and you have 100 customers. People tried shortcuts. Adapters bolt little extra layers into the network, but those layers run in sequence with everything else, so every prediction gets a little slower, forever. Prompt tuning steals some of your input space to stash task instructions, but that eats the room you needed for actual context. Both trade quality or speed for size. LoRA refuses the trade. Here's the key bet. Fine-tuning changes the weights by some amount. Call it delta W, the total nudge. The weights themselves are huge and complicated. But the nudge? The paper's hypothesis, the nudge is simple. It lives in a tiny number of directions. Formally, delta W has a low intrinsic rank. Even when the matrix is 12,000 numbers wide, the actual change might only need a rank of 1 or 2. And a low-rank matrix has a cheat code. You can build it from 2 skinny ones. Instead of learning the full delta W, a giant D by D grid, you learn B, tall and thin, and A, short and wide. Multiply them, B times A, and you get back a full-size update, but you only ever stored and trained those 2 slivers. If R is 4 and D is 12,000, that's not a rounding error. That's thousands of times fewer numbers. So the layer now has 2 paths. The original frozen weights W0, untouched, never trained. And the new detour. Push the input through A, then B, and add the result on top. Output equals W0 times X, plus B times A times X. The big model still does the heavy lifting. The little BA just leans on the wheel. One beautiful detail makes this safe. Start a random, but set B to exactly 0. So on step 1, BA is 0, the detour contributes nothing, and the model behaves exactly like the pre-trained one. You never lurch away from a model that already works. You gently steer it. Then training only ever touches A and B, a tiny fraction of the weights, so you skip storing optimizer state for the billions you froze. And the savings are not subtle. Now the part that beats adapters. At deployment, you just add BA into W0 once, one addition, and you're left with a single weight matrix the exact same shape as the original. The detour vanishes into the road. Inference runs at full speed, byte for byte like a normal model. 0 added latency by construction. And to swap tasks, subtract this BA, add a different one. Hot swap a personality in milliseconds. If make the giant model tiny to customize is the kind of trick you're here for, like, subscribe, and send this to the friend still saving 100 full copies of the same model. Quick bit next, which weights and why rank 2 is enough. You don't even LoRA the whole network. Just the attention layers, really just the query and value projections, and freeze everything else. And the rank? Absurdly small. Even for the biggest GPT-3, a rank of 4 matches full fine-tuning, and rank 1 often gets there. The update the model needed was hiding in almost no dimensions at all. Why does so little work so well? When they cracked open what BA learned, it wasn't inventing new features. It was amplifying ones the frozen model already had but wasn't leaning on. Fine-tuning for a task, it turns out, is less learn everything again and more turn up the few knobs that mattered. LoRA just gives you exactly those knobs. So the whole recipe, freeze the giant. Bolt on 2 skinny matrices, B times A. Start B at 0, so you begin right where the model already is. Train only those slivers. Fold them back in at the end for zero latency inference, and a task file you can email. Same quality as full fine-tuning, 10,000th the size. Which leaves one open question worth chewing on. If the change a task needs is this low rank, what does that say about how much a pre-trained model already knows, and how little learning a new task really is? That's my read. Tell me yours. Until next time.